You know when you're watching an ice cube melt in a glass and you just take it for granted? Well, there's actually a super deep physical puzzle hiding in there. Today, we're going to dig into a new theory that might just flip what you thought you knew about temperature on its head.
So here's the mystery that's always kind of bugged physicists. When you add heat to ice, the molecules start breaking free. They start moving around a lot more, which means they have more kinetic energy. So why does a thermometer in that water just stubbornly sit at 0 degrees Celsius until every last bit of ice is gone? All that energy's going in, but the temperature isn't budging. What's going on?
Okay, so the explanation you probably got in high school science class is pretty simple. It's this idea of latent heat. The story goes that all the energy you're adding is being used up to do one job and one job only, breaking the bonds that hold the ice crystal together. It's too busy to make the molecules move faster, so the temperature stays put. Seems plausible, right?
Well, here's where that old explanation kinda hits a wall. The research we're looking at today points out a huge flaw. Think about it. Once a water molecule breaks free from the ice, it is moving faster. It has more kinetic energy than it did when it was locked in that crystal. So if temperature is just the average kinetic energy, the temperature should be going up. That contradiction tells us the textbook story is, well, it's missing something big.
And this brings us to the really wild idea at the heart of this new research. Maybe the problem isn't with the ice cube at all. Maybe the problem is with how we've been defining temperature itself. We might just be measuring the wrong thing.
So here it is, the central claim from this paper by Jerry Z. Liu that basically turns the old idea inside out. Temperature isn't really about how fast molecules are bouncing around. Instead, it's about the energy they radiate. You know, the heat and light they actually give off. This actually makes a lot of sense if you think about it. An infrared camera doesn't measure how fast molecules are moving, it measures the radiation coming off of something.
Okay, so let's break that down. Instead of thinking about temperature as a speedometer for molecules, think of it more like a light meter. And what's fueling that light and heat? It's not the motion. It's the potential energy stored in the bonds between atoms and molecules. That is a fundamentally different way of looking at this.
And you know what? There's some pretty compelling evidence for this. The classic kinetic theory is great at predicting how much energy it takes to heat up single atoms, but it completely fails with more complex molecules. And as this graph shows, that missing energy, the part the old theory just can't explain, lines up almost perfectly with the number of bonds in the molecule. The energy was hiding in potential energy the whole time. So, if potential energy is the real star of the show here, what's the actual mechanism down at the tiny, tiny scale that moves all this energy around? Well, the paper proposes this really cool new concept to explain just that. It's called a transimpact. And here's the best way to picture it. An atom absorbs a little bit of energy. One of its electrons gets all excited and jumps to a higher energy level. When that happens, the atom itself suddenly puffs up. The paper calls it an explosive popcorn-like burst, and it gives its neighbor a massive shove. Let's walk through this visual. So in frame A, you've got two atoms just hanging out. Then in B, an electron in one of them gets excited and jumps to a higher orbital, making the whole atom expand. See that? That expansion creates this huge repulsive force. And by frame C, it's literally blasted the other atom away. This isn't some gentle push. It's a powerful, instant kick. And this isn't just some obscure theoretical thing. According to this theory, these little transimpacts could be the secret engine behind a whole bunch of phenomena we already know about. You know, the random jiggling of pollen in water called Brownian motion? That could be it. The way a Crookes radiometer spins in the light? That too. Even the heat you feel when you rub your hands together could be driven by these tiny atomic explosions.
Okay, deep breath. We've redefined temperature as a measure of radiative energy, and we've got our engine, the transimpact. Now let's put it all together and go back to our melting ice cube to finally, hopefully, solve this whole thing.
All right, here's how it all comes together. First, you add heat. That energy gets soaked up by the bonds between the water molecules, and it stretches them out like tiny little springs. But, and this is the absolute key, those bonds can only stretch so far before they just snap. They hit a maximum limit. This creates a hard ceiling for how much potential energy the system can hold. And since that potential energy is what generates the radiative energy we measure as temperature, the temperature gets capped or anchored right there at 0 degrees. It physically cannot go any higher until all those bonds are broken.
You know, a really strong theory doesn't just explain the normal stuff. It has to explain the weird exceptions too. So let's look at a couple of strange phase transitions where the temperature isn't constant and see if this new model can actually handle them. So on the left, we've got helium doing this bizarre thing where it becomes a superfluid with zero friction at unbelievably cold temperatures. And on the right, we have one of those chemical hand warmers that gets hot when you click the little metal disc inside. Both are phase changes, but they act totally different from our ice cube. So what's the deal? Why aren't their temperatures anchored? Well, for helium, the whole thing happens as it gets colder. You're taking energy out, not putting it in, so there's no competition for where the energy goes. The temperature just keeps dropping. The heat pad is the complete opposite. When it crystallizes, it releases energy so fast and so chaotically that the system is totally unstable. You don't have those slow, steady conditions you need for the anchor to form, so the temperature just skyrockets instead.
And this actually leads us to a really neat way to categorize phase transitions into two types. You've got bond-limited ones, like melting and boiling, that happen at a specific temperature when all the bonds are stretched to their absolute max. And then you have impact-driven ones, like evaporation or sublimation, when ice turns straight into vapor. Those can happen at lower temperatures and are caused by a single, powerful transimpact, just knocking a molecule loose. So after all of that, what's the big takeaway? It's this. That constant temperature you see when ice is melting has basically nothing to do with kinetic energy staying flat, because it doesn't. It is a direct result of the potential energy stored in all those molecular bonds hitting its absolute maximum limit. That limit creates a ceiling, an anchor for the radiative energy that we measure as temperature.
And that really leaves us with a pretty mind-bending thought, doesn't it? We think of something like temperature as so basic, so figured out. But if a completely new perspective can solve a puzzle that's been hiding in a glass of water this whole time, it really makes you wonder, what other fundamental facts of science are just sitting there, waiting for someone to look at them in a completely new way?